Hi, this is Alex from devstories.eu. OpenCV Computer Vision Deep Dive, Episode 9 of 20. For a decade, the biggest bottleneck in real-time object detection was not the neural network itself. It was the clunky, hand-coded algorithm used to clean up its messy, overlapping predictions. The solution to this is YOLOv26, specifically its end-to-end NMS-Free detection architecture. To understand this shift, you have to look at how traditional detectors finish their job. They rely on non-maximum suppression, or NMS. NMS is a slow post-processing step. When a standard model looks at an object, it does not predict just one bounding box. It predicts dozens of overlapping boxes around the same object. NMS steps in to score these boxes, calculate their overlap, delete the duplicates, and leave only the single best fit. This cleanup process is inherently sequential and almost always runs on the CPU. Picture deploying a vision model to an NVIDIA Jetson Orin for a warehouse sorting robot. You need to detect hundreds of fast-moving packages at 60 frames per second. The GPU blazes through the neural network layers, then the pipeline stalls. The CPU chokes trying to run NMS across thousands of raw overlapping box coordinates. Your frame rate plummets because of the cleanup, not the inference. YOLOv26 eliminates this bottleneck entirely by providing native NMS-free inference. You pass an image into the network, and the network outputs exactly one box per object. The post-processing script is gone. To make this possible, the YOLOv26 architecture drops a component called distribution focal loss, or DFL. In previous iterations, DFL was used to model the edges of a bounding box as a continuous statistical distribution. It helped the model guess where fuzzy or obscured edges might be, but it naturally encouraged the network to output multiple overlapping guesses. Removing DFL fundamentally changes the network behavior. Without it, the model is heavily penalized during training for predicting more than one box per object. It forces the network to be absolutely decisive. However, removing DFL creates a new problem. Forcing the network to output exactly one hard boundary makes the training process highly unstable. The loss landscape becomes sharp and chaotic. To fix this, YOLOv26 integrates the MuSGD optimizer into its training pipeline. MuSGD stabilizes the learning process by dynamically adjusting the momentum based on the variance of the gradients. When training hits a steep, chaotic part of the loss landscape, MuSGD dampens the weight updates so the model does not derail. When the gradient path is stable, it accelerates. This specific optimizer is what allows the architecture to converge on a single strict prediction without collapsing. The result at deployment is massive. When you export a YOLOv26 model to TensorRT for that warehouse robot, the entire pipeline stays on the GPU. The network processes the frame and directly outputs the final package coordinates. The CPU is completely freed up for other robotic control tasks. Here is the key insight. The fastest code is the code that never runs. By shifting the burden of deduplication from a runtime post-processing script back into the optimization phase of training, YOLOv26 unlocks hardware efficiency that was previously impossible. That's all for this one. Thanks for listening and keep building.